Hey guys, so today we're going to talk about a couple of different types of nuclear decay. In chemistry, most of the reactions we deal with things like sticking atoms together to make larger molecules, like this reaction right here for the synthesis of water. When we do reactions like this, we balance the reactions to make sure there are the same number of atoms on each side. So we start off and finish with the same number of each type of atom. We also deal with reactions where we break molecules apart, something like this. Okay. So here again, we start off and end with the same number of nitrogen and hydrogen on each side. We also deal with a lot of reactions where atoms kind of swap places in molecules. So we might have something like this. And there are many variations of these types of reactions, and these are the type of reactions that we'll deal with for the majority of this class and almost in all chemistry situations. Just simply the rearrangement of atoms to make either more large and complex or smaller and less complex molecules. But while we're on the subject of atomic structure, particularly the structure of the nucleus, we want to talk about a special class of reactions that we call nuclear reactions or nuclear decay. So these are a special class of reactions that actually violate one of John Dalton's postulates in his atomic theory. When nuclear reactions or nuclear decay reactions, those terms are kind of used interchangeably, when they occur, we actually convert an atom of one type of element to an atom of a different type, or a different element, So we know that each element is defined by having a specific number of protons in its nucleus. So carbon, for example, always has 6 protons. So if we do have a nuclear reaction where we change carbon into something else, we know we have to change the number of protons somehow, because as long as carbon has 6 protons, whether it's carbon 12, carbon 13, carbon 14, and so some different isotopes of carbon, they all still have 6 protons. The mass difference is reflected by the change in number of neutrons here. Okay, so this specific isotope of carbon would have 6 neutrons, this would have 7 neutrons, this would have 8 neutrons. So one other thing we want to point out here before we get started about the nuclear symbols is this is the standard way to write carbon 12, but it's also common to write it like this, where 6 is just the atomic number. We often leave that 6 off because what element it is tells us the atomic number. So without that 6 being there, I can look at the periodic table, see that carbon has 6 protons without needing to know. But if I do write it like this, I have the mass on top and the number of protons or the atomic number on bottom. So a lot of times in nuclear reactions, when we're writing them, we'll actually go ahead and write the number of protons present, and that kind of makes writing the reactions easier. So there are 4 major types of nuclear reactions that we're going to look at. Before we get started, a couple of terms we need to talk about and get used to. So you have a reaction, let's just say we have a generic element X, and it goes to elements Y plus Z. Okay? So obviously in a reaction like this where the elements change, we can't balance the reaction as we typically have to make sure there are the same number of atoms on each side for each particular element. So in these types of reactions, what we try to do is that make sure that we have the same mass on each side. So if we have an atomic mass of 13 over here, we might have an atomic mass of, let's just say, 9 here and 4 here. So that's what we look at in these types of reactions, is we try to conserve or balance the mass of each reaction. So one other term, the reactant side of the arrow, so the left side of the arrow, the atom or species that undergoes nuclear decay, we will call the parent nuclide. So that's just the species that undergoes decay, and the resulting either 1 elements or 2 elements that are present after the decay we call the daughter nuclides. So if you're asked about the daughter nuclides for a particular type of decay, then you're simply being asked what is the product of the reaction there. So many of the reactions we'll deal with later in the class, we have a lot of specific rules to tell us exactly what type of reaction is going to happen, and we can predict the products. So nuclear decay is a little bit different. So certain elements and certain isotopes of that element are known to undergo certain types of decay. And really the only way to know that is to basically memorize, what elements undergo what decay. We determine experimentally what type of nuclear decay is going to occur. So it's obviously way beyond the scope of this class to worry about, what elements going to undergo what type of decay and in what situations. That'll always be given to you, and unless you go on to pursue a career in nuclear physics, you'll likely never be tasked with that. So we often associate nuclear decay with things like uranium and the transuranium elements, the very heavy elements. But it turns out that very light elements, things we deal with in our everyday life like neon and calcium and potassium and carbon, also undergo nuclear decay. They just undergo different types of nuclear decay, and only certain isotopes of those elements undergo nuclear decay. So just as a review, again, an isotope of an element, or isotopes rather, are just two atoms of the same element that have a different number of neutrons and therefore have a different mass. So let's go ahead and jump in and look at the four major types of nuclear decay that we're going to look at. So the first type of nuclear decay we're going to look at is through a process called alpha particle emission. So the symbol for an alpha particle, or an alpha particle emission here, is the Greek letter alpha. Okay? So an alpha particle is equal to a helium nucleus. Okay? So there's the typical helium nucleus, so a helium-4 nucleus. So we can also write an alpha particle as this, helium-4. Okay? And I can also go ahead and write that 2 right there. That just tells us that helium has 2 protons. But I also need to note that it's only the helium nucleus. Okay, so it's only the protons and the neutrons, so it's not the electrons included there. So this would have a positive 2 charge. Okay? So we very rarely write that. That's what an alpha particle is, though. An alpha particle is simply 2 protons and 2 neutrons, which is equivalent to the helium nucleus. But instead, we typically write it like this, the alpha symbol with the 4 and the 2. So the 4 tells us the mass, the 2 tells us the number of protons, so we have 2 protons and 2 neutrons. So we could write the plus 2 charge here because it does in fact have a positive 2 charge, but for the most part that's simply understood. Okay, so what actually happens in an alpha particle emission, or we often refer to it as alpha decay. So in alpha decay, we can say an alpha particle is ejected from the nucleus. So we have this large nucleus. It's actually small, but it's of a larger element most likely. So we can say it's composed of many neutrons and protons, and I'll just draw in several. So for many different reasons that are way beyond the scope of this class, there's some type of energetic imbalance here that causes an alpha particle to be ejected. So we have that, and what leaves is an alpha particle. So it's 2 protons and 2 neutrons. So it's a small particle that is equivalent to a helium nucleus. So if we think about what we have left over now, we'd simply take the original number of protons, subtract 2, the original number of neutrons, and subtract 2. So let's look at an example here. So we have Am-241. So that might not be an element that you're familiar with. It's americium is the name of the element. You can guess what it's named after. And it's typically used in smoke detectors, industrial and home smoke detectors. It's actually a fairly common element in industry one that you might not realize, but probably is actually in your home or has been in your home at some point. So the atomic number for americium is 95. So I won't go in detail here on how smoke detectors work, but part of the process that allows smoke detectors that contain americium to work is that americium-241 undergoes alpha decay. And so if it undergoes alpha decay, it's going to eject an alpha particle. Okay? So if americium, which has 95 protons, loses 2 protons, it's not americium anymore, because americium atoms always have 95 protons. So if it loses 2 protons from the nucleus, we have to go to the periodic table and find its new element, or what new element it is rather. Okay, so 95 minus 2 is 93. So if you go to the periodic table and find element number 93, you find it is neptunium, Np. Okay, so we have the 93. Again, we don't have to write that in, but it makes it a lot easier to check our work here when we're done. So the original mass was 241. We lost 4 mass units in the form of 2 protons and 2 neutrons. So 241 minus 4 would be 237. Okay. So now we need to go back and double check and make sure we have the correct mass on each side. So 237 plus 4 is 241. I started with 241. So in alpha decay, the number of protons is conserved. So I can say number of protons is conserved. So that means that we start and end with the same number of protons. So 93 plus 2 is 95. But this is only for alpha decay. This doesn't apply to all situations because protons aren't always conserved. So now this applies only to this specific example. So if I wanted to label this, I could say this is the parent nuclide, this is the daughter nuclide, and this is an alpha particle. Okay. So that's one of the more common types of decay, and it is one of the easier to write out and balance there. So now let's look at the second type of decay. So the second type of decay is we'll call decay through beta particle emission. Or we'll commonly just call this beta decay. So the symbol that we use to represent this is the Greek letter beta with a minus sign there. Okay? So beta particle decay is a little bit different. So for beta decay, in the nucleus of the parent nuclide, you actually have one neutron is converted into one proton. Okay? So I know that's kind of a strange concept, but just kind of trust me here on this one. How that actually happens is a very high level concept that we'll save to discuss for a different class here. So not at this level of chemistry. So in this case, every time we have a beta particle decay or a beta decay, we're not going to end up with the same number of protons. Okay, we're going to convert one neutron into one proton. So if an element gains one proton, it is no longer that element anymore. It's actually become a different element. So let's look at an example. Let's say we have carbon 14 undergoes, we'll call it beta decay. Okay. So what I would ask you to do is write the formula for the beta decay of carbon 14. So to start off, alright, carbon 14. Now go ahead and write the 6 down here. It makes it easier to go in and check my work. So I know that if I have a beta decay, one neutron is being converted into one proton. So neutrons and protons have the same mass. So if all I'm changing is a neutron to a proton, the mass isn't going to change here. So the mass of my daughter nuclide should be the same, 14. But if I'm gaining one proton, I have 6 protons, I gain 1, I then have 7 protons. So I go look at the periodic table, and I see that element 7 is nitrogen. So then you actually have another product that we'll write in, but we won't worry about that. We want to worry mostly in this course about the original nucleus and the daughter nucleus, what actually changes here. So let's go ahead and label these. Here on the reactant side, the parent nuclide, I have 6 protons, and then I have 8 neutrons. Okay? So on the daughter side, I have 6 protons. Excuse me, I don't have 6 protons. I have 7 protons because the atomic number changed. So that means I also have 7 neutrons. Okay? So we're changing the number of protons and the number of neutrons here because they're being converted one to the other. So then next I want to look at what is called a positron emission or a positron decay. Okay, so a positron emission, the symbol for that is a capital beta with a plus sign. It is the exact opposite of a beta emission. So a positron emission, 1 proton converts to 1 neutron. Okay, so the exact opposite process here. So let's look at an example of this. So I can have magnesium 23. Okay, and if I know magnesium 23 is going to undergo a positron decay, I know 1 proton is going to become 1 neutron. So I know the mass is not going to change here because protons and neutrons have the same mass. But I know that 1 proton is going to be converted. So now I only have 11 protons. So if you look at element 11 on the periodic table, you find sodium. So you actually have a few other products here. You have a positron, plus you have a positron neutrino that we're really not going to worry about. So I just write these to make you aware that they're there. If I ask you to solve this problem, I wouldn't require that you write this here. I'm more concerned about the parent and daughter nuclide here. So if I wanted to go and label this, the parent nuclide has 12 protons. The daughter nuclide has 11 protons. So that means that the parent nuclide here has 23 minus 12. So it has 11 neutrons. And then the daughter nuclide would actually have 12 neutrons. Okay? So here, mass is still conserved in both of these. I have a mass of 14, stays a mass of 14, a mass of 23, stays a mass of 23, but I don't conserve the number of protons because I actually convert 1 proton into 1 neutron or 1 neutron into 1 proton there. So if I give you a nuclear reaction and ask you to tell me what type of decay was undergone, then you look at, first I'll see an alpha particle. If you see an alpha particle being emitted, then you know it's an alpha decay. Then you look at the number of protons. Okay, so look at the atomic number. Did the atomic number increase by 1 or did it decrease by 1? And hopefully that will be able to tell you, did it undergo a positron emission or a beta emission. Then the one last type of nuclear decay that we'll talk about briefly is simply gamma decay. So you see that typed out as a Y. It's supposed to be the Greek letter gamma. And it simply releases energy, okay? So we really won't talk about gamma decay here. Gamma rays are very high energy, and this type of decay is used in industry and medicine some, but for now, just be aware that gamma decay releases energy, and that's really all you need to know about it for now. So mainly we want to focus on the alpha decay, the beta decay, and the positron decay. So again, these aren't reactions that we encounter very often because they're not something that we can force to happen. It's something that a specific isotope just does on its own. The only way that we can force it to happen is by creating a certain isotope, which we actually do in the case of nuclear energy, which we will discuss later. But the main thing you should be able to do now is identify the 3 major types of decay and then write the reaction. And just keep in mind, this is the only time in chemistry that you'll ever encounter reactions where atoms can change from one type to the other. And the examples that I give you and you see in textbooks are very, very specific examples that only apply to that one situation. So you can't take, carbon, for example, and do something to it and turn it into gold. So these atoms decay into very specific types of atoms, and only certain types of atoms and isotopes undergo this decay. So just be aware of that. So let's look at a couple of examples in your notes. I believe number 20 says radium 226 undergoes, I believe it says alpha emission. I don't have it right in front of me. Whatever it says though, we'll go with alpha emission. So the first step, no matter what the problem is as far as writing a decay process, we have radium 226. And I know because it's radium that it has 88 protons, so I go ahead and write that in. That kind of helps me with the process. So it undergoes alpha decay, so I know one of the daughter nuclides, or one of the products, is going to be an alpha particle with a mass of 4 and 2 protons. So if radium loses 4 mass units and its original mass is 226, the mass of the other daughter nuclide is going to be 222. If it had 88 protons and the nucleus lost 2 protons, the new nucleus is going to have 86 protons. If you go ahead and write radium again, you're going to be wrong here, because a nucleus that has 86 protons is no longer radium. You look at the periodic table and see that it's actually radon. Then I go back and check myself. 222 plus 4 is 226. 86 plus 2 is 88. So I'm correct there. There is my nuclear reaction. So let's look at one more. Let's look at the first part of number 24, where it says Cobalt 60. Let's see, undergoes, I believe it says beta emission, or beta decay here. So if I look at my original problem, I have Cobalt 60. I look at the periodic table, see that Cobalt has a mass of 27. Now I think, okay, what does a beta decay do? So a beta decay, I remember, converts 1 neutron to 1 proton. So I know my product is going to have 1 extra proton. But I know if it changes a neutron to a proton, then mass doesn't change. So it has the same mass here. So if I look at the periodic table, I see element number 28 is nickel. So there's the main thing I'm concerned about. I also could go in and write the other products, but we're going to leave those off for now. I'm more concerned about the parent and daughter nuclide. Just be aware there are other products that you'll discuss if you ever study nuclear physics at a higher level. Okay. So I can also write that out to say Cobalt 60 decomposes into nickel 60. Okay. There's multiple ways to write that, but we'll tend to write it with the symbols. So here we see that the number of protons changes, is not conserved. But that's okay, because we know that in the beta and positron emission that the number of protons isn't always conserved. So that's kind of a crash course of nuclear chemistry. That's really as far as we're going to get in this course. It's an interesting topic. We'll discuss how this relates to nuclear energy in a bit. But I'm going to make one more video about this, and we'll talk about kind of the rate these reactions happen, so how quickly they occur.